Einstein's kinematical definition of simultaneity, appealing to the constancy and invariance of the velocity of light, implicitly characterizes the relativistic, so-called Lorentzian inertial frames within which Maxwell's equations are now true. And Einstein's principle of equivalence characterizes the privileged state of freely falling motion, in terms of which the mathematical geodesics of the variably curved space-time geometry of the general theory first acquire an empirical or physical, not just mathematical, significance. The result is a relativized neo-Kantian conception of scientific rationality or objectivity that develops and changes with the progress of empirical science. But this, as I've also argued, is very similar to the relativization of objectivity to paradigms during Kuhnian scientific revolutions. Indeed, it is not only the case that the transition from Newton to Einstein is Kuhn's main example in chapter 9 of his book, Structure of Scientific Revolutions, of what he takes to be conceptual incommensurability, but Kuhn's historiographical approach more generally has clear roots in the neo-Kantian tradition, in the work of such thinkers as Emile Meyerson, Alexander Poiré, and once again, Ernst Cassirer. It is no surprise, therefore, that Kuhn took to characterizing his conception as what he called Kantianism with movable categories. And very late in his career, he also recognized its kinship with the relativized a priori found in early logical empiricism. On this basis, I have reinterpreted the problem of Kuhnian conceptual incommensurability in more Kantian terms. The problem is that Einsteinian relativity articulates a radically different space of conceptual possibilities, both mathematical and physical, that were simply impossible relative to Newtonian theory. Things became possible that were not possible. In particular, whereas one can indeed represent the structure of Newtonian gravitation theory as an approximate special case of Einstein's theories, by, for example, letting the speed of light go to infinity and considering the solar system as an isolated system not affected by anything outside it, so-called island universe, we can then get the center of mass of that little island to be a Newtonian inertial trajectory, and there will be a gravitational potential there, uniquely defined in that frame, which is a Newtonian potential. So we can do that. We can embed the Newtonian theory as a special case of Einstein's. Nevertheless, the possibility defining constitutive principles of Newton's theory in such a limiting argument, the laws of motion, come out as mere empirical conditions holding in a parochial approximate limit, namely in this limit of this special situation. And therefore, they no longer appear as constitutive, as possibility defined. They're just empirical things that happen to hold if you have a little region that's enough like that. So we can thereby uniquely define the Newtonian inertial frames and gravitational potential, as I suggested, but only relative to a now entirely contingent distribution of matter. So it's not, in any sense, constitutively a priori when you take it to be a limitless way. In that sense, the possibilities are radically changing. The problem then becomes explaining how a new space of conceptual possibilities can rationally evolve from an old one. And I have addressed this problem in turn by a historical narrative depicting the various and intricate ways in which the mathematical and physical developments leading from Newton to Einstein were inextricably entangled with a parallel set of developments within scientific philosophy, principally involving Mach, Helmholtz, and Poincaré, as you may know. All of whom, in one way or another, continue the original Kantian legacy in a revised form and explicitly do so. The upshot of this narrative, by an argument that is too long to summarize here, is that a cutting-edge turn-of-the-century classical physicist, such as Henri Poincaré, had very good reasons in his own terms for taking Einstein's expansion of the classical space of conceptual possibilities seriously, for accepting it, that is, as itself really possible. This is how, beginning with Kant, that went by very quickly. Okay, there'll be time for discussion. This is how, beginning with Kant and his relation to Newton, I have been first led to the importance of Hilbert-style implicit definitions in explaining how our fundamental mechanical concepts of space, time, and motion acquire their empirical meaning, then to the relativized a priori and its connection with Kuhn's theory of scientific revolutions, and finally to a solution to the reinterpreted problem of conceptual incommensurability, which emphasizes the mediating role of scientific philosophy. Enough about me. Let's hear about Mark. Mark Wilson's philosophical journey began when he was a student of Hilary Putnam's at Harvard in the late 1960s and early 1970s. He was attracted to the new theory of reference articulated by Kripke and Putnam, and promulgated in Putnam's The Meaning of Meaning in 1974, and by the robust scientific realism within which Putnam at that time placed this theory. Wilson was convinced early on, however, that this new theory of reference was much too simple-minded in such pronouncements as water refers to H2O, for example, and that more generally our ordinary terms of macroscopic conceptual classification relate to the physical world in a much more complicated fashion than that. Wilson's voracious reading in the history of physics and mathematics, engineering, the theory of differential equations, as we know by now, and virtually every other subject concerned with how the physical world and language actually work, including the theory of color and paint manufacture and you name it, then propelled him on an incredibly detailed and breathtakingly original investigation of these matters of word-world relations. The first fruit was his great paper, Predicate Means Property, in 1982. The latest is Wandering Significance, appearing, as I said, in 2006. Here, in Wandering Significance, Wilson sums up his relationship with Putnam in quotation number 6, which is too long for me to read or for you to read. But notice at the end, he doesn't like the water equals H2O by baptizing this liquid, whatever it is. Liquid, he says, after all, behaves even more irregularly in its predicative fixity than water. In any case, the supportive fabric of facade I shall defend displays rather different characteristics than any scheme that Putnam contemplates, and certainly not the simple theory of reference scheme. In short, Wilson accepts Putnam's early scientific realism and related project of delineating the actual word-world correlations exhibited in our linguistic behavior, especially our scientific linguistic behavior, but he replaces the simple-minded correlational mechanisms envisioned by Kripke and Putnam with what Wilson calls the supportive fabric of facade. Wilson focuses on predicates of macroscopic physical classification, concepts such as force, hardness, rigidity, and redness, all of which have been taken to be problematic in various ways since the birth of classical physics in the 17th century. Red, of course, was problematic because it was a secondary quality. Continuous macroscopic bodies, as opposed to the point particles or point masses of traditional Newtonian mechanics, became subject to mathematical physical treatment during the 18th and 19th centuries, principally through the mathematical theory of partial differential equations. This theory then led to some of the most beautiful and important developments in 19th century mathematics. Fourier series, complex analysis, Riemann surfaces, Sturm-Liouville existence and uniqueness theory, which in turn, these developments, eventually led to the development of modern set theory as the overarching framework within which solutions to such equations can be rigorously established and investigated. So that's why for Mark, unlike someone like Klein, set theory is important because it gives you the existence and uniqueness theory of partial differential equations, not because it's a general framework for thought. And at the same time, the evolving mathematical theory of partial differential equations played an essential role in the description of macroscopic matter in classical continuum mechanics, where the essentials of Newton's conceptual apparatus were extended to this new realm. Newton basically operated with point mass mechanics, and indeed actual distance